Assalamu alaikum to all, and welcome to our online lecture series for the course Design and Analysis of Algorithms. In this lecture and the next, we shall be learning about dynamic programming, sometimes shortened as DP. Dynamic programming, as you may recall, is one of the three main algorithm design techniques that we said we will teach in this course. Now we have already learned about divide and conquer approach. So now dynamic programming is next, and after that we shall study greedy algorithms. Now here is the outline for this particular lecture. First, we explain what dynamic programming is all about. Then we discuss the steps that are generally followed in designing algorithms using this approach. We then go into the subject in more detail by solving example problems using the DP approach. We shall take two main examples in this lecture and two more, or maybe one more in the remaining lecture. So we start by looking at an algorithm that you are very familiar with from data structure, which is the Fibonacci sequence. See how we can solve it using dynamic programming. And then take our first major example, which is the rod cutting problem. This is the one we're going to use actually to show in detail all the steps that are normally followed in solving a problem using the dynamic programming approach. Some of the terms I will be listening here may not be making sense until we learn about them. We will learn about optimal substructure, recursive top-down solution, and then we look at the dynamic programming solution of the same problem using two approaches, top-down and bottom-up. We will look at sub-problem graphs as a way of determining the efficiency of the dynamic programming algorithm. And then finally, we will look at how to reconstruct a solution based on the algorithm design using the dynamic programming approach. Okay, as I said, some of this may make more sense after we look at them, but this is just showing you the sequence of how we will approach this second example. Now let's try and see what dynamic programming means. First, we note that dynamic programming is an algorithm design technique that is generally applied to optimization problems. That is, problems that involve finding a minimum or finding a maximum. And as we may know, such problems usually have many possible solutions. The solutions are not unique. Okay. The second point to note is that dynamic programming is actually very similar to the divide and conquer approach that we have already learned. Like divide and conquer, DP also solves problems by dividing them into sub-problems, solving the sub-problems, and then combining the solutions to form the solution to the original problem. However, it has a big difference compared to the divide and conquer approach. Unlike the divide and conquer, here sub-problems are not independent. You can only apply DP to divide and conquer problems for which the subproblems are overlapping. So the subproblems are not independent. All right, the subproblems must overlap before you can apply dynamic programming on them. So unlike divide and conquer that can work in both cases, whether the subproblems are dependent or not dependent, for dynamic programming, we can only use it if the problems are not independent, or in other words, if the problems are overlapping. And if the problems are overlapping, you will find that using dynamic programming gives you a much better algorithm compared to DC. DC will do much more work solving the overlapping problems repeatedly, whereas the dynamic programming will only solve each subproblem only one time, avoiding repetition. This is actually one of the main advantage of DP compared to DC. Okay. So in summary, that explains actually what dynamic programming approach is. It is simply an algorithm design technique that is designed to improve on divide and conquer by solving overlapping problems only one time, saving these solutions to the subproblems, usually using an array the first time they are solved, and reusing these solutions if the subproblem is encountered later again in solving the problem. Yeah. So this is basically the idea of dynamic programming. The word programming is misleading actually, because it's not a programming per se. It is simply a design technique in which we use a table to store solutions to problems that we encounter, so that when we encounter them again, we don't recompute. We just use the value that is computed before. So because these values are being computed dynamically, this is why they call it dynamic programming, but it's really not a programming, it's just an algorithm design technique. Good, so that is about what it means. Of course, we shall see and understand it in more detail after we have taken examples. Now, what are the steps followed in applying this algorithm design technique to solve problems? The first step is actually to characterize the structure of an optimal solution. This actually means deriving a formula, if you like, or an equation that can be used to compute the optimal solution. And such a formula, as we shall see, must have a property called optimal substructure. We shall explain what this means in detail. But basically, the first step is to generate an equation or a relationship that you can use to compute an optimal solution. The second step is try to come up with a recursive algorithm that can evaluate the formula that you have generated in step 1. Okay, so recursively define the value of an optimal solution. The next step is, after coming up with the recursive algorithm, usually you will find that it is not efficient. So it is at this point that you now try to improve it using the dynamic programming approach. And there are two ways of doing it, either top-down or bottom-up. For all the examples that we shall be seeing, we will solve them in both approaches, using the top-down, sometimes called memoization, and bottom-up. Okay, the last step, step number 4, is constructing an optimal solution from the computed values based on the algorithm in step 3. Yeah, so essentially this means tracing to find the options or the routes that are followed in obtaining the optimal solution. Again, this will make more sense actually after we take an example. But the one thing to note is that this last step may not be necessary for all problems. Sometimes it is needed, sometimes it is not. But usually the first 3 steps are required. But step number 4 may or may not be needed. Because if you are just looking for the optimal value, we have already obtained it from step 3 using the algorithm we designed. But if you want to know how that optimal value is obtained, then you need to do the last step. This step number 4 will help you to reconstruct and see what options were followed to obtain the optimal solution. Okay, now we're going to study this by examples, starting with the very simple example that you are already familiar with, the Fibonacci sequence. As you will recall, these are the sequence in the Fibonacci. Basically, the first 2 values are given, they are 1 and 1. And then after that, the subsequent values are computed by computing the sum of the last 2. So here 2 is obtained by adding 1 plus 1. 3 is obtained by adding 2 plus 1, and so on. So if you like numbering the elements from 1, this is number 1, this is number 2, number 3, and so on. This is the recursive algorithm for evaluating these values, as we already know from the data structure course. Now, I should emphasize with reference to the steps we enumerated earlier for solving the DP problem, this is actually step 2, coming up with recursive algorithm. This is because the first step in this case is trivial, because the formula for Fibonacci is already known. We don't need to define it or derive it. But for other problems, as we shall see, we actually have to first derive the formula, then we come to this step of coming up with the algorithm. Now, the algorithm is very easy, as we already know. It simply checks if n is either 1 or 2, meaning if it is element number 1 or element number 2, we just return 1. Otherwise, we just return the sum of the element computed with n minus 1 and the n minus 2. Now, in terms of efficiency, the running time, as we all know, for this algorithm is very, very bad. The running time for n is the running time for n minus 1 plus the running time for n minus 2. And that means this function, the running time, will actually grow exponentially, since it basically doubles as n increases. It will give you big O of 2 to the power n. The reason why it is giving you that, of course, is because of the repetitions involved, as we remember the recursive tree. So, for example, for n minus 2, it is computed twice. N minus 3, or f of n minus 3, or fib of n minus 3 is computed 3 times. Fib of n minus 4 is computed 4 times, 1, 2, 3, 4. And the repetition increases like that as you go to smaller values. This is actually what makes this algorithm to be very, very bad. You can imagine, for example, if n is 1000, then the call with 1 is going to be computed 1000 times. and then the call with 2 will be computed 9 times, 999, and so on. All right. Now the next step, having seen that this normal recursive algorithm is very poor because of the repetition, the next step is to see if we can come up with a DP algorithm that will try to avoid repetitions. But before that, we have to ask ourselves the question, can DP be applied to this problem? The answer is obviously yes. Yes, because one, the problem is defined in terms of subproblems. Yeah, this is requirement number one. It has to be represented in terms of subproblems. The second issue is that the subproblems are overlapping, as we saw. There are many repetitions, and therefore DP can be used to avoid these repetitions. This diagram emphasizes the condition under which we can use DP and the condition under which we must use divide and conquer. The DP will not help us. So if the subproblems are independent, then DP is not applicable. In any case, the divide and conquer will do quite well, actually, because there are no repetitions. On the other hand, if the subproblems are overlapping, then dynamic programming approach will give you a much more efficient solution. So let us see how we can now use DP to improve on this recursive version of the Fibonacci sequence. The idea basically is to compute the values for the smaller values of n, and the values of the function for the smaller values of n first. Save them in an array or a table so that when you encounter them later, you simply reuse them. Yeah, this is what the bottom-up approach will use, and that is the one we're going to see first. As we said, there are two versions, either top-down or bottom-up. So the bottom-up will start with solution to the smallest problems and then build the solution up to the larger problems by reusing the already computed solution for the smaller problems. Right. Now this is the DP version of the algorithm. As you can see, it is using an array to save the values for element number 1 is going to be 1, element number 2 is going to be 1 also, and then the next set of elements are computed by simply reading from the array. So for I equal to 3, for example, it's going to be the value at position 1 and that of I minus 2. Basically the previous two solutions which can be obtained from the array, and so on until n. So you can see that here no value is computed more than one time, and this is the power of dynamic programming. What do you think will be the running time of this algorithm? Obviously it's going to be big O of n, because each element is computed only one time. Okay, now let us look at the other approach, which is called top-down using memoization. The top-down actually is a slight modification to the recursive algorithm. In other words, we're still going to use recursion. However, we're going to improve it by using an array to store the values that are computed, so that when we encounter the same n, we just read the value from the one that was computed earlier. All right. So as we said, like the bottom up, a subproblem fib of k, where k is less than n, is only going to be computed one time. And this technique is called memoization, coming from the fact that we are remembering the previous solutions. This is the memoized version of the Fibonacci sequence. It breaks the algorithm actually into two. The first one will create an array which will be used to actually save the solution and initialize it, in this case with -1. -1 because we know that valid values for the Fibonacci are all positives. So if you see -1 in a particular cell, we know that that value has not yet been computed. This is the idea. So we create an array and initialize all the cells to -1, and then call this second method or procedure, passing to it the array that has been initialized here and the original n that we wish to find its Fibonacci. Okay. Now the second method here has two important differences if you compare it with the recursive version. It is recursive quite okay, because as you can see there are two recursive calls. However, if you look at this first statement, it is checking. Is m at n, the n we are trying to find its Fibonacci, is it not computed before? If yes, then go ahead and compute it. But if not, meaning if it was computed before, don't do anything, just return the value at n. This is the big difference. So for all values of n that were computed before, we will never have to compute them again. Just come straight here and return m at n. On the other hand, if the value is still -1, meaning it is not yet computed, then we follow the algorithm. If n is 1 or 2, again here there is a big difference. We don't just return m at n, even though we know the value. Rather, we save this value. Okay, and eventually we're going to return it. Okay, even for the recursive case, we don't just say return the recursive call with n-1 and recursive call with n. No. Do the recursive call and save your result first, then return it. Okay, so even though this looks similar to the recursive version, actually this is much more efficient, because this recursive call will terminate immediately if the value was computed before. It will come directly here. Yeah, so this is what is called memoized version of the dynamic programming. We still leave the method as recursive. However, we now use an additional parameter, which is an array, to keep storing the values. And then the algorithm itself is updated to first check. If the value was computed before, then don't bother computing it again, just return the current value. Right, what is the running time? Obviously, it is again big O of n. Why? Because for each call, we are only going to do the computation one time. There is no repetition. So the running time is exactly as that of the bottom-up approach, linear. Okay, so that's what we are saying here, that like the Fibonacci DP or the bottom-up, the memoized Fibonacci also compute each value only one time. So in other words, although there are recursive calls, all those recursive calls for which the value is already known will simply terminate immediately. So that's what is meant by this crossing. All those second or more recursive calls are not actually going to execute. They are just going to be terminated by returning the value in the array. Right. So that's our trivial example using the Fibonacci, and I hope it gives you an idea of the dynamic programming approach.